I hope I'm audible to all of you and my whiteboard is visible to all of you. First of all, I'm asking a participant to write their student ID in the chat box. So please write your student IDs in the chat box. Okay, so my today's discussion is on solving a system of equation. Solving system of equation. And as you know that I told you that I would be discussing module 4 and module 3 simultaneously. In my last class, I discussed about the first part of the module 4, that is the definition of vector space. And I hope that you are practicing the chapter 1 of the book and trying to figure out how we can find that given a system is a vector space or not by checking whether the system satisfies all the properties, all the 8 properties that has been discussed in my earlier class. Solving system of equation is also somewhat connected to vector space, but the connection that I'm not going to talk about right now. Connection will be discussed in some later classes after we do a considerable amount of topics in this vector space chapter, and you will get to see how these two things are connected. Let us, for the time being, study the two things as if they are separate. So let's discuss about solving system of equation, and for which I'm taking a very simple system, which is as follows, which is x plus 2y is equal to 1, and twice x plus y is equal to -1. Very simple system with 2 equations and 2 unknowns. 2 equations are there and 2 unknowns are there. And we know that in this particular type of systems, the solution is always unique. Solution of the system is always unique. And you can apply various process by which you can solve the system. Here, the process that I'm going to define is the approach that I'm going to talk about is the matrix approach, matrix theory approach. The first part of the approach is actually known to you, but for the completeness of my discussion, I shall be recapitulating the things by which this system can be solved using matrix theory approach. So what we actually do, the procedure number 1, let me write it in the following manner. Process 1. So if I want to go with the matrix approach, what we actually do is that we try to write the system in matrix form. So we write Ax equal to B, where capital A is actually the coefficient matrix, where I choose the coefficients of the variables from each of the equations. The first row of the matrix is the first equation, the second row of the matrix is the second equation. In the first row, we write 1 and 2 because 1 is the coefficient of the variable x and 2 is the coefficient of the variable y. In the second row, we write 2 and 1, which is the coefficient of the first variable x in second equation, and 1 is the coefficient of variable y in the second equation. And to find out, and also capital X is the column matrix which is given by xy, and small b is the matrix which is on the right hand side, which is given by 1 and -1. So this is how we actually represent the matrix. We actually can multiply the matrix to get back the original system of equation. Now, to solve it by matrix inverse method, the process 1 that I'm going to talk is called the matrix inverse method. What we actually do, we try to find out whether the matrix is singular or non-singular. So step number 1, it is the checking of whether the matrix is singular matrix or non-singular matrix. whether A is singular or non-singular. If it is non-singular, that means the inverse of the matrix will exist. And this checking can be done by finding out the determinant of the matrix capital A, which is calculated in the following manner, which is equal to -3, and therefore it is not equal to 0, and therefore A inverse exists. A inverse exists. Okay. In step number 2 that we are going to do is the following. We are going to find out the adjoint of A. Now, adjoint of A is actually the transpose of the matrix of the cofactors of the matrix capital A. So what we actually do to find the adjoint of A, we find the cofactor of the elements of the matrix capital A, and we take the transpose of that. We form the matrix and we take the transpose. So how we do this? In matrix capital A, the cofactor of the element 1 will be -1 to the power 1 plus 1, because it is its position. First row and first column, first row and in first column, 1 is actually residing, and omitting this row and this column, the remaining element or remaining matrix here, the remaining element, because the matrix is a 2 by 2 matrix, this is actually that means the minor of 1 is considered, preceded by a sign with respect to which the element is occurring. So this is the cofactor of the element 1. Similarly, the cofactor of the element 2, since 2 is residing on first row and second column, so we write -1 to the power 1 plus 2, and we consider the minor of these 2. The cofactor of this 2 will be -1 to the power 1 plus 2, 2 plus 1, that is second row first column, and its cofactor will be, its minor will be there, that 2, and the last one will be the element -1 to the power 2 plus 2, that is, since the element 1 is occurring at second row and second column, and its minor will be that one. So it will be like this. And if we calculate, we will find that the first element is positive, so we write 1. The second element is negative, so we write -2. Third element is negative, so we write -2, and the fourth element is positive, so we write 1. Okay, and we take the transpose of that, and ultimately we get the adjoint of A to be the following: 1 -2 -2 1. Actually, the transpose of the matrix here is the matrix itself. Okay, so we get the adjoint as follows. Step number 4 gives you, step number 3 gives you the formula for calculating the inverse of the matrix. So what we do, the formula is given by the following. It is adjoint of A divided by determinant of A, and determinant of A is -3, so we write 1 by -3, and this multiplies the entire matrix 1 -2 and -2 1. So the inverse of the matrix is -1/3, 2/3, 2/3, and -1/3. These are the inverse. This is the inverse of the matrix. Now, once we find this, then we consider this equation once again, and we know the inverse of the matrix exists. So what we do is the following. We know that capital A into X is equal to B, and since A inverse exists, so we can multiply both the sides by A inverse as follows, and then we can associate the two matrices A inverse and A together, and A inverse A is the identity matrix. So from there we get X equal to A inverse B. So this is the formula by which the matrix capital X can be found. Okay. Now you just take the screenshot of this page because I'm going on to the next page. This is my page 1. This is page 1. In the next page, I'm going to continue solve with this particular problem. Okay. So my page 2 contains the following. So as we have capital X equal to A inverse into B, now we can substitute the inverse of the matrix, which is minus 1/3, 2/3, 2/3, and minus 1/3. And we can multiply this inverse of the matrix by the matrix 1 minus 1. Okay, by the matrix B. So we have 1 minus 1. And on the left hand side, that is X, we have the column matrix XY. Okay, and the order of the matrix is 2 by 2, and the order of this matrix is 2 by 1. So definitely the order of the matrix, order of this product of the two matrix will be a matrix of order 2 by 1. And here the matrix of the matrix is of the order 2 by 1, so that we can correlate the left hand side and the right hand side. Now what we get actually, so we get, if I multiply the two matrices, I'm doing the operation over here. We get minus 1/3 into 1 plus 2/3 into minus 1. This operation gives me minus 1/3 minus 2/3, which is minus 3 by 3, that is minus 1. So I'm writing here minus 1. And the second multiplication gives me 2/3 into 1 plus minus 1/3 into minus 1, which gives me 2/3 plus 1/3, which is equal to 1. So we get 1. And since the order of the two matrices is the same, so we can equate the corresponding elements. So from there we can say that X equal to minus 1 and Y equal to plus 1. This is the solution of the given system of equation. Now you can check whether the solution is correct or not by substituting the values over here. If X equal to minus 1 is substituted over here and Y equal to 1 over here, we get 2 minus 1, that is 1. So first equation is getting satisfied. If you put X equal to minus 1 over here and Y equal to 1 over here, we get minus 2 plus 1, which is equal to minus 1. Both the equations are being satisfied, and therefore this is the answer to our given problem by matrix inversion method. This is one type of the solution that you can consider. And the second process that we can talk about to solve the same system of equation is actually called the determinant process. The determinant process goes like this. We have the system, I'm again writing the system, which is X plus twice Y equal to 1 and twice X plus Y is equal to minus 1. And after that, you can write it as X, Y, in this manner you can write, and 1. In the denominator over here, you can put the determinant 1, 2, 2, 1. Here in the denominator below X, you are going to replace the column 1, 2 corresponding to the X by the column 1 minus 1. So in place of 1, 2, I'm going to write 1 minus 1. And the remaining one will remain will be same. It will not be changed. So it is 1, 2, 1. And in this particular position below Y, you are going to keep 1, 2 fixed, and you are going to change the column 2, 1 by 1 minus 1. You know what I'm talking about. This particular rule is actually called Cramer's rule, and probably you have learned this rule in your school days. Those who do not know Cramer's rule, I'm again saying what I'm doing over here. First of all, by looking into the solution, I'm writing the thing in the following manner. I'm writing X by something, Y by equals to Y by something equals to 1 by something. Okay, that is the process. This is step number 1. In step number 2, what I'm doing is the following. Someone has written that the Cramer's rule and previous one is Martin's rule. There are actually various different names, but I mean, these names can, if you can recall the names, then it's okay, no problem with that. If you do not recall the names, at least try to recall the process by which the thing is done. Okay, so Martin's rule, that name that you have written over here, most of the students are not familiar with this particular name, because in books, Martin's rule is, some books nowadays authors use this, but in many other books you can find that this name is not mentioned. Cramer's rule rather is actually called, is much more famous than the name Martin's rule. Okay, and it is, these names are actually used because of the person who actually devised the rule. Now, okay, so step number one, we actually do this kind of thing. We replace the column 1, 2 of this matrix by 1 minus 1, the right hand side. And here we replace this column 2, 1 by the right hand side. So we get ultimately this. And then from this type of equation, we can write x to be the determinant 1 minus 1, 2, 1. And divided by 1, 2 and 2, 1. So this is the value of x, and y is equal to determinant 1, 2, 1 minus 1, and that is 1, 2 and 2, 1. This is the value of y. And if you can find the, if you find the determinant, you will probably get the same result. So let us just try to find it out because of the completeness. So in the numerator, you are going to get 1 minus 2, that is plus 2. And the denominator, you are going to get 1 minus 4. So ultimately, what you are getting, 3 by minus 3, that is minus 1. The same was coming over here. And on the right hand side of that, you are getting minus 1, minus 1, minus 2, that is minus 1, minus 2, that is minus 3. And in the denominator, you are getting 1 minus 4, that is minus 3. So which is 1. So you are getting the value of 1, y as 1. Okay, so the same values are actually can be found by using Cramer's rule also. So I have showed you the two methodologies by which this particular simple equation can be solved. Now here is a question for you. Now let me see who can answer this question. I have discussed these two problems in matrix inversion method and the Cramer's rule because they are mentioned in the syllabus. Okay, I will not discuss any more problems on that because these things are known to you. My question is something else. My question is, can you tell me what are the drawbacks of these two methods? What is the main constraint or restriction on these two methods? The matrix inversion method, you will say that, okay, the matrix has to be a non-singular matrix. That is definitely a constraint, but I'm not asking about that constraint. That constraint has already been discussed with you. I'm asking about something else. My question is, what are the fundamental constraint on applying the previous rules? Can you tell me what is the fundamental constraint? Yeah, very good. The one student has written it correctly. The fundamental constraint on applying the previous rule is that the matrix has to be a square matrix. Matrix has to be a square matrix. This is the main drawback. This is the main fundamental restriction. Major calculations, Srijita, what do you mean by major calculations? Someone raised his hand. What do you want to say? But unmute yourself and ask me. Who raised his hand? What do you mean by major calculations? Major calculations in mathematics, in higher mathematics, many operations are there which are containing major calculations. So here, by major calculations, I don't understand what do you mean.
No, sir,
Bolo?
I meant to say that it applies a higher number of calculation steps, which can lead to mistakes in the last.
To me, the matrix inverse, there is no difference between matrix inversion method and Cramer's rule with respect to the higher number of steps. If the size of the matrix is increasing, to do it by Cramer's rule or to do it by matrix inversion method actually requires same amount of labor. So this is not the actual answer. The actual answer is the other student that Preeti has written in the chat box, that the main drawback of these two methods is actually the matrix has to be a square matrix. Now, this is the constraint. Now, see, if the matrix is a rectangular matrix, then we cannot find the inverse of the matrix, because rectangular matrix inverse cannot be found. Now, I am asking another question, that what do you think that that the system of equation that we are considering will always be squared? Yes or no? When we talk about the matrix, when we say that the matrix is a square matrix, that means what? The number of variables and number of equations, they are same. Then only the matrix is a square matrix. Okay, so do you think that in the system the system will be dealing with will always be a square matrix? No, because there might be systems where the number of variables, there might be systems where the number of variables and number of equations, they are actually not same. They are different. Now, one may be greater than the other. Okay, as the case may be. So in some cases, the number of variables is greater than the number of equations. In some other case, the number of variables now is less than equal to the number of equations. Now, my third question is that if we have question number 2, if we have the scenario 2 represented by question 2, how can we deal it? How can we deal with the system? What is your reply? What is the process by which you can deal with the system if such a scenario happens? Can we solve it or will be stuck? BH matrix, okay, by matrix approach. Now, which approach you are going to apply over here? Some student has written by matrix approach we can do. Which approach you are going to apply over here? First one.
The first one.
First one, but the first one is requires the matrix to be a square matrix. How will be able to apply this approach? Because I told you that in my case the number of equation, number of variables are not same. That means the matrix is rectangular. So how will be able to apply the first approach? Yeah, so this answer is not known to you. You have successfully given me the answers to the previous 2 questions. Yeah, Gaussian elimination method. Gaussian elimination method, probably you are thinking that I'm going to discuss Gaussian elimination method because it is in the syllabus. It's in syllabus, Gaussian elimination method is written. So I'm not going to mention, I was not going to mention this name over here. This high voltage name, I try to always keep myself aloof. my simple methodology to deal with such a situation is actually known as the rank method. I will talk about the rank method now. Rank method, and you have come across the this type of methodology. Yes, rank method. So in this type of methodology has already been discussed with you in my prerequisite class when I tried to find out the inverse. But here, since I'm going to explain how to apply rank method to solve a given system of equation, first of all, what I'm going to do is the following. I'm not going to talk about any system consisting of unequal number of equations and variables. I am going to discuss the same rank method for the problem which I have been discussing since the beginning of the class. So my question is x plus 2y, which is equal to 1, and 2x plus y is equal to -1. So my process 3, by which I'm going to find out the solution, is actually known as rank method. I'm going to explain this to you right now. As usual, the matrix is given by the following. The equation is given by the following matrix representation, and let me write the matrix representation over here: 2, 1, and here the column matrix is xy, and here the column matrix is 1, -1. Okay. If you are thinking of vector space, I'll say that this is a vector, this is a vector, this is also a vector. Remember, this is also a vector. Okay, so this is the thing. What I'm going to do is that I'm going to find out some equivalent form of the given matrix capital A. To find out a equivalent form, an equivalent form, let us call this equivalent form to be some suitable equivalent form. I shall omit this word suitable later on. Right now, let us stick to this particular word, suitable. So I will find out some suitable equivalent form for this matrix capital A by the rank technique. And first of all, let's see what is happening. So we have this matrix 1, 2, 2, 1, and if I want to find out the rank of the matrix, then what would be my methodology? My methodology is the following. My methodology will be the following. The technique is try to find out an upper triangular matrix, first you try to find out an upper triangular matrix. That particular matrix, this particular method is actually called the forward pass method. Forward pass method. And with some sort of row operation and column operation. And the second stage that I'm going to apply is the following. The upper triangular matrix is transformed into a special form. It is called reduced row echelon form. It is called reduced row echelon form by making the first non-zero entry of each row the only non-zero entry of that column. only non-zero entry of that column. Quickly take the screenshot because this class is going to end. I'm going to continue in the next session.
We join again, sir.
Yes, yes.